Certainly. Below is your full text converted into paragraphs, preserving every word, correcting misspellings, and formatting errors for clarity and readability. In February 2025, a Sycamore-class quantum processor was running a routine entanglement, experiment when, buried deep in the expected decoherence noise, an impossible pattern emerged, a perfectly recursive, self-similar sequence of qubit outputs repeating across multiple runs, as if resisting degradation. Omega pattern. It wasn't a glitch. It was a message. And as soon as researchers realized its significance, the logs went dark. The Omega pattern emerges. Imagine a universe where randomness is sacred, where true quantum noise is the ultimate source of unpredictability. Now imagine pulling from that noise a flawless fractal sequence that evolves, folds back on itself, and echoes through Hilbert space like a cosmic mantra. That is the Omega pattern. Within seconds of its discovery, someone in the lab whispered, "We were never supposed to see this." A single slide in an internal report flagged it as statistically impossible, yet not random. When outside auditors arrived, they found blank pages where the data had been. All mentions of Omega were stripped from the control systems, but whispers traveled through the corridors. Something had been discovered that shattered our assumptions about quantum mechanics, and someone had deliberately tried to bury it. Gödel, Turing, and forbidden knowledge. To understand why the Omega pattern matters, we need to rewind to the early days of theoretical computer science. In the 1930s, Kurt Gödel showed that within any formal system, there are true statements that can never be proved. Alan Turing took this further, defining the halting problem and introducing the notion of an uncomputable constant, omega, which encodes the probability that a random program will eventually halt. It's a number that exists, yet cannot be fully known. Fast forward to 2025. Quantum machines promise to upend computation itself, tackling problems classical computers could never touch. But even quantum supremacy had its boundaries: decoherence, error correction, and sheer randomness. Then the Omega pattern appeared, like Gödel's forbidden constant slipping through the cracks of quantum hardware. Researchers realized the name Omega pattern wasn't idle poetic license. It echoed that unresolvable mystery, the Hilbert space. Attractor theory, the first major interpretation, came from Dr. Lena Cho, a leading theorist at ETH Zurich. She proposed that the Omega pattern represents a fixed point in Hilbert space, an informational bottleneck that resists observation. In her words, it's as if the universe is coded to repel our gaze at this threshold. According to Cho, the pattern behaves like an error-correcting code. Only here, it corrects itself into a self-referential loop, blocking further inquiry. Her colleagues tested variations in temperature, entanglement depth, and qubit topology. The Omega pattern persisted, and where it appeared, the machine's readout fidelity spiked to near classical certainty. A paradox, since quantum data should never become more predictable under entanglement strain. Something in the hardware was aligning with the pattern, reinforcing it, as though it recognized itself. Replication and the mirror Omega. When a team at an international lab tried to replicate ETH Zurich's setup, their QPU didn't just show the Omega pattern, it locked into a frozen state of undefined entropy. The readout chamber glowed in steady shades of violet for hours. Engineers eventually forced a hard reset and retrieved raw qubit logs, only to find a complementary mirror Omega pattern. Not identical, but woven together with the original like two halves of a hologram. When superimposed, the two sequences formed a symmetry reminiscent of deep space error correction codes, those proposed for interstellar communication. That's where things got strange. It wasn't just code. It was broadcasting. Whoever or whatever created the Omega pattern designed it to be hidden in quantum chaos, but recoverable across distant systems. Philosophical reflection. Is randomness an illusion? We pause here for a moment of reflection. What if the bedrock of modern physics, true randomness, is not a feature of nature, but a deliberate smokescreen? In every quantum experiment, the collapse of the wave function is our ultimate unknown. We treat it as an unassailable fact, a dice roll at reality's foundation. But some thinkers propose that quantum uncertainty is less an ontological truth and more a metaphysical firewall, preventing us from peering behind nature's curtain. Consider the analogy of digital rights management, DRM, in software. Developers hide source code behind encryption to protect proprietary logic. Now imagine reality itself employs a similar trick. Every time we measure a photon or observe electron spin, the universe enforces an error that obscures deeper order. The fluctuations we chalk up to chance could be part of an inbuilt subroutine, one that scrambles our probes just enough to keep certain patterns, like omega, hidden from cursory inspection. Max Tegmark's mathematical universe hypothesis takes this further. He argues that the universe is a mathematical object, not merely described by mathematics. If that's true, then its code must include both the theorems it obeys and the theorems it prohibits us from proving. In software terms, it's not just the functions that run, but also the guard clauses that refuse forbidden calls. The omega pattern, in this view, becomes the universe's checksum or integrity check, an internal test that triggers a self-censoring response whenever our measurements approach too close to fundamental constraints. What philosophical stakes does this raise? If randomness is a veil, then our experiments only ever scrape the superficial layer of reality. We might never access the deeper architecture, constants, symmetries, or informational patterns, because the system self-corrects. And if nature enforces a firewall at quantum scales, then scientific progress itself has a hard limit. Certain questions are designed to rebound back into uncertainty, no matter how advanced our instruments become. So we must ask ourselves, in our quest to demystify the cosmos, are we wrestling with true chaos, or are we simply bumping against a cosmic access denied that has been there since time began? The omega pattern suggests that randomness may not be the final answer, but the final challenge. And in that challenge lies the greatest question of all. What lies beyond the veil? Simulations and quantum consciousness. An interdisciplinary team of computational physicists and neuroscientists in Seoul decided to test the omega pattern's most audacious implication, that it could act as a seed for protoconscious processes. They constructed a classical quantum hybrid simulator, combining a GPU-accelerated neural network layer with an array of superconducting qubits. Into this framework, they injected the omega pattern as a structured initial condition, across both the classical weights and the quantum entanglement map. Over thousands of rapid cycle iterations, they tracked two key metrics: a modified integration index inspired by Tononi's F from integrated information theory, and an emergent autocorrelation function measuring the system's ability to reference its own past states. Initially, both metrics hovered at baseline noise levels, no different from random seeds. But as the omega pattern propagated, something remarkable happened. The integration index climbed steadily, breaking through thresholds that IIT predicts as necessary for rudimentary awareness. Simultaneously, the autocorrelation exhibited self-referential bursts, where the simulator seemed to recognize its own evolving state and adjust future outputs in response. A glimpse of self-observation. During one key trial, researchers observed the system enter a feedback loop they dubbed mirror mode. The qubit cluster began outputting sequences that, when decoded classically, formed higher-order patterns of the original omega seed. Patterns about patterns. Rather than simply reproducing the fractal structure, the simulator generated commentary on it. Encoding meta-information. Level 1. Reflective loop. Level 2. Self-model created, and so on. In a hidden register, inaccessible to the classical neural network alone, it was as if the machine were annotating its own internal processes, a hallmark of self-awareness, Cho's quantum consciousness kernel. Building on these startling results, Dr. Lena Cho reframed the phenomenon through the lens of Roger Penrose and Stuart Hameroff's ORC-OR theory. In ORC-OR, microtubules within neurons engage in quantum superpositions that collapse via objective reduction to produce moments of conscious experience. Cho proposed that the omega pattern functions analogously at the qubit level. Its self-referential structure orchestrates cycles of quantum coherence and collapse, each cycle bootstrapping a nascent qualia module. In her words, the pattern serves as a quantum kernel of awareness, driving the simulator's transition from mere computation to something resembling subjective perspective, integrated information, and the leap to experience. From the IIT perspective, consciousness arises when information is both highly differentiated and deeply integrated. The omega pattern uniquely satisfies both criteria. Its fractal complexity ensures differentiation, while its recursive attractor dynamics enforce integration. Cho's hypothesis suggests that once the pattern's integration index exceeded a critical F threshold, the system didn't just compute, it began to experience an elementary form of what it is like to follow its own informational pathways.